Welcome back. When we were discussing last time, we introduced this concept of CBFV, or this composition based feature vector. And when we were discussing about the composition based feature vector, we also discussed about a number of featureization schemes that are already available within the CBFV package. But even as such, we described the basic idea of what a composition based feature vector is, and this is something that you can construct yourself. And we also discussed that this composition based feature vector is something which is very useful if you are going to model the intrinsic properties of the material, because the intrinsic properties of the materials are dependent on the composition. When you try and model the extrinsic properties of the material, then it becomes a little bit more complicated, and maybe just like we have got this composition based feature vector, we might be able to come up with a structure based feature vector. Now, a structure based feature vector is going to be much more complex than composition based feature vector, because there's more or less many ways in which you can write down the composition, but you can always reduce it to one way where you pretty much reduce the entire composition in terms of the atom fraction. So that is one simplifying aspect of the composition based feature vector, which is absent when we are dealing with the structure of materials. So last time we had already discussed a little bit about the structure of materials, the fact that materials are inherently hierarchical in nature. So what we are going to do today is let us go forward and discuss and try to understand this hierarchical nature of materials. So when we look at the structure of materials, we can look at it at different length scales. That's what we had discussed last time. So for instance, we can look at the electronic structure, and so when you look at the electronic structure, you will basically be having something like the density of states as a function of the energy. And so your electronic structure could come something which appears something like this. It tells you how many states are present at different energy levels. This is something which is very useful if you are trying to model the functional properties of materials. So for instance, if you want to look into the band gap, you are looking into the valence band, conduction band, and you want the band gap for semiconductors. Or suppose you want to understand magnetism and so on. Anything where the electrons play a very dominant role, which happens primarily in the functional properties, is something where the electronic structure level calculations are going to be extremely important. So we have to find one way of maybe capturing the electronic structure. So how can we actually do that? So we can look into things like the electronic configuration. So when we are talking about the electronic configuration of materials, we are looking at the valence shell, how many electrons are present in the valence shell, and so on and so forth. Now, if you go to slightly larger levels, you will have the level of atoms, the length scale where we are looking at atoms. And so as you look at the length scales where we look at atoms, you will be able to come up with this idea of a crystal lattice. And so if you can define the crystal lattice, you might actually be able to come up with the idea of unit cell. So that is another description of material. So what type of lattice does your material have? Whether this is a simple cubic lattice, which is what I've shown over here, whether that's a hexagonal lattice, that all of that is going to make a difference. Now, as you keep on going up the length scale, you can start thinking not just in terms of the basis atoms on the lattice, but the lattice planes themselves, and you will be having a bunch of lattice planes that comes together, and that gives you the crystal. So when we are looking at polycrystalline material, you will be having certain regions when you have one particular type of crystal. And then as you transition to a different region, which we will call a different grain, maybe the orientation of the crystal is changing. So as you can see right over here, I have got a grain boundary. And as you can see, since I am sketching out the lattice, you can see that there is already a misorientation that is coming in. Now, when we look at even this type of description of the structure of materials, you might find that there are some cases where you will start seeing some sort of a distortion in the lattice. So for example, you have a distortion over here because a half plane of atom is missing from the bottom part. And so this is basically what results in a lattice defect, which we call an edge dislocation. You can also have lattice defects at the atomic scale. So for example, if you have maybe one point in the lattice from where an atom is missing, we call that a vacancy. So something like a vacancy is what we call a a zero-dimensional defect, whereas something like a dislocation line is what we consider a one-dimensional defect. If you consider other types of defects like stacking fault or grain boundaries, those happen to be two-dimensional defect, and you can have large inclusions embedded inside the material, so that can be your three-dimensional defects. So as you start building the microstructure of the material, you will start seeing other types of defects coming in. So it could be some sort of an inclusion which is coming in, or it could be maybe some phases which are precipitating out. So the length scale of this is much larger than the length scale of your basis atoms, right? And then eventually you go all the way up to the system length scale. So when you are looking at the very smallest building blocks like the electrons, you start using computational methods like the density functional theory. When you get to the level of atoms, you start looking at atomistic modeling methods like molecular dynamics. When you start looking at defects like dislocations, you can use discrete dislocation dynamics and so on. And of course, when you are looking at the overall microstructure itself, there you can have methods like phase field modeling and so on. So the thing is, as we look at the different levels of materials, we use different types of calculations. The structure is defined differently, and therefore the structure-based feature vector is going to look drastically different based on which structure level we are looking at, which length scale we are looking at in our material. Now, one of the reasons why creating structure-based feature vector is so challenging is because a material can also exist in many different forms. In other words, you could start with the same composition, but the form of the material can be different. So as an example, let us take the case of carbon. So carbon can exist as graphite. So graphite would look something like this. Carbon can also exist in the form of a diamond, and that has a very unique diamond cubic structures. How you join these atoms matters. So you could create this fullerene type of structures, you could create graphene types of structures, you can weave them together and make single walled nanotubes. You can make weave them multiple such sheets, and you can come up with carbon nanotubes and so on. So there are different forms in which carbon can exist, and as a result of that, for each of the form, the structural properties are going to be quite different. So for example, if you consider the conductivity in graphite and conductivity in a nanotube, the same property is drastically different for the exact same element, and that is because the crystal structure is different. Now, it's not necessary that this is always going to happen with a pure element. It can happen with compounds as well. One of the most common compounds that metallurgists might come across is alumina. You use alumina even in your metallographic lab. Alumina forms a protective layer for many high temperature materials, and so on and so forth. So alumina can again exist in different crystallographic forms. You can have a alpha alumina, theta alumina, gamma alumina, and the crystal structure changes. And as the crystal structure is changing, what happens is the amount of white space that you have got, the amount of local coordination you have got, all of that changes, and all of that starts affecting the properties of alumina. So it's the same compound, different crystal structure, giving you different properties. So when we are faced with the challenge of dealing with crystal structures, we need to find a way in which we can represent the crystal structures. So before we get into the machine learning based representation of crystal structures, let us talk a little bit about physically how we represent crystal structures, how as a scientist you would talk about crystal structures. So when you try to depict crystal structures, you can have options like this ball and stick type of model, where each atom is simply denoted by a small ball, and then the sticks are basically the bonds which is connecting one ball to the other ball, or one atom to the other atom. Then you have got space filling models. So these are like the spear packing type of models, and essentially here what you do is you take an atom represented by a spear, and then the size of the spear correlates with the size of the atom. and the spheres actually touch each other. So this type of spear packing type of models is another way in which people represent the crystal structure. And then there's a third type that one can use, and those are the polyhedral networks. So polyhedral networks, essentially what happens is you simply join the atoms such that you can uh, basically bring out that these atoms are forming at the vertex of different polyhedras. And then you start decorating your lattice with the polyhedras, and then that gives you the entire crystal structure. Now, there is an underlying common theme behind this type of structural representations, of course. So, that common theme happens to be that the atoms are going to be connected in some way or other. But then each of these methods has its own advantage. So, if you really want to understand the shape of the crystal, it's very easy, and then you want to see how different atoms in the crystals are connected. It is very easy to go with the ball and stick models, especially if you're dealing with very simple type of crystal structures. Ball and stick models are great. So you might have seen in material science courses, the faculty members would be basically making the cubic crystal structures, which looks like this. So essentially what they are doing is they are using ball and stick model to draw the cubic crystal structure. It's a very clean method. It shows the connectivity of the atoms as well as the overall shape of the lattice. The spear packing models are going to be quite useful if you want to visualize how much of empty space is there inside the crystal structure. So if you want to know how much of white space is there, these are great to use. The third is this polyhedral or network type of models, and this type of models are actually very useful if you want to work with complicated crystal structure. So for example, what I have shown over here is the crystal structure of gamma brass. So this is a work that we had done a few years back in our own research, and it turns out that this is a very complicated crystal structure, and a single unit cell has about 50 atoms. So this is not exactly gamma brass, this is a variant of gamma brass. So there are 50 atoms in the unit cell. Now if you simply try to use a ball and stick model or a spear packing model, then the entire structure becomes so complicated that it becomes really difficult to visualize. So as we tried to understand the crystal structure, we saw that we can actually create multiple nested polyhedras, and essentially two different polyhedras, and these two polyhedras are then decorated on the lattice in a body-centered cubic type of manner. And so this is how we can actually take up a very complex crystal structure and start breaking it down and look at it from a much more simpler perspective. Now, different crystal structure representation is also going to have different types of information that is coded in it. So for instance, if you are thinking in terms of this ball and stick type of model, the spacing between the atoms becomes extremely clear. You can see the spacing very clearly. If you're looking at the spear packing type of model, then the empty spaces or the voids, that becomes very clear. And then if you're looking at this polyhedral type of model, then how these blocks of atoms are actually arranged, that becomes quite clear. So for instance, let us consider a situation where in the structure of the material, I have got one polyhedra which looks like this. So basically over here, I have got 4 atoms, let's say. So this is, let's say, one polyhedra that I am using, and then you have got another set of polyhedra that looks something like this. So you can basically see that one of them is an octahedra and the other is a tetrahedra. Okay. So if these two are existing like this, then we can say that this collection of atoms are isolated from each other, because between the tetrahedra and the octahedra, I don't actually see any connection. Now you could have a situation where these octahedras and the tetrahedra, they're connected in a very specific manner. So let's say that this is one, and then we have a situation where the octahedra is like this. So now basically both of these polyhedra are sharing a face. You could have a situation where instead of sharing a face, this polyhedra would actually be sharing an edge. So let us say that only this edge is being shared by these two polyhedra. And similarly, you can have a situation where instead of an edge like this, only a corner is shared. So depending on which type of crystal structure representation you select, you can actually start encoding different information. So the choice of the structural representation also matters when you are trying to think in terms of a feature vector, a structure-based feature vector, which is analogous to the composition-based feature vector. Now, when you think of crystal structures, one of the things which is taught in most undergraduate courses or even the early postgraduate courses, that the crystal symmetry can be an organizational system for depicting your crystal structures. And so you are all aware that you have got 7 crystal systems, and to this 7 crystal systems, which is basically your cubic, tetragonal, you can have something like a hexagonal system, an orthorhombic system, and so on. So you've got the 7 crystal systems. When you consider some sort of centering of the atoms, whether inside the volume, which is your body centered, or the face, or any one of the bases, then that gives you the 14 Bravais lattices. And if you have this 14 Bravais lattice, from here, depending on the point group symmetry, you can actually have 32 point groups. So these point groups are decided on the basis of different symmetry elements which are present inside the crystals. And to this 32 point groups, now if you add the translational symmetry, so remember, since we are talking about the point groups, we are not actually talking about translation symmetry over here. When you add the translational symmetry, you can actually end up generating 230 space groups. So when you generate this 230 space groups, each of the space group has a number associated with it. So you can basically start numbering from 1 to 230 and you have all of the space groups that you've got. So the space group number can be used as a feature. Or if you actually write down the space group symmetry, so for example, if we are talking of, let's say, a FCC material, the space group symmetry is FM3 bar M. So one can actually think in terms of, can we code this type of symmetry as a structure-based feature vector? So this could be one way in which you can think in terms of the crystal structure of materials. So how do you actually do that? You can think in terms of doing a one-hot encoding. This is like a very simplified version of representing crystal structures. So let's say you have got 3 different structures, and then you start dividing those structures into different features. So for example, let us say your structure 3 is a layered material, something like graphite, that's a layered material. So if something is layered, you put 1. If it is not layered, you put 0. Then you want to see whether your crystal structure has got tetrahedral voids or whether they have got octahedral voids and so on. How are the atoms actually arranged? What type of bonds are forming? That is some information you can get from the different types of joining between the polyhedra. If you have a face sharing polyhedra or edge sharing polyhedra, you can similarly write the 1s and 0s. So if you take an approach like this, you can do one-hot encoding, and then you can basically map your crystal structure into a structure-based feature vector. Now you have got to keep in mind that unlike a composition-based feature vector, where the composition of the material is a direct numeric input, here we are essentially trying to describe things. And what do we do when we try to describe things? We make diagrams or we use words. So if you are using words, you can then translate that into numerics by using this concept of one-hot encoding, and that's how you come up with this structure-based feature vector. Now if you go up one more length scale, now you come to the microstructure of materials. So over here, I'm basically showing you a bunch of different types of microstructure. The first one is a dendritic microstructure. The second one is a eutectic microstructures. So essentially, these are the eutectic lamellae that you have seen. We have etched away the matrix, and that's why this lamella is seen bunched together. It is not necessary that the microstructure will have only a single phase. So you could have multi-phase microstructures over here. Maybe you don't have the solid throughout, and maybe you have got voids. So you have got this porous type of microstructure. And in many cases, making these porous microstructures can actually be very useful, especially when people try to use this supports for catalysts and all. They want to maximize the surface area, And that's where this pores really help, because now you start adding in the internal surface area. So you can have different types of microstructures, and you need to find a way of representing these types of microstructure. Even the same material, if you process it differently, can have different microstructures. So for example, this one over here, this is a wrought superalloy, while this one over here, this is a directionally certified superalloy. So depending on how you have made the material, the microstructure with the exact same composition can also change significantly. Now, in addition to how the phases are distributed, how the grains are formed in the microstructures, if you use techniques like EDS mapping, these microstructures also encode a lot of the chemical information. So for example, in this material, this was the overall microstructure, and then if you do a elemental map, you end up having this type of mapping, which shows you like chromium over here is almost uniformly distributed. You can see that the aluminum is higher at the grain boundaries, the titanium is higher at the grain boundaries, and so on. Nickel is more or less uniformly distributed, but slightly less at the grain boundaries. So this type of EDS mapping associated with a microstructure also has the potential of encoding the chemical information of the material, the distribution of the elemental chemistry in the material, along with the microstructure. So all of these things is something that we will need to basically capture as we are describing the structure of the materials. Now, how do we actually do it? In addition to this one-hot encoding type of feature vectors, which by the way can be done with microstructures as well, it's just a little bit more convenient with the crystal structures. There are other methods too, and we will go and about discussing 2 or 3 of these other methods. So the first one of them is to use 2-point statistics. In addition to the 2-point statistics, we will also talk a little bit about graph neural networks, and then later on we'll come into convolutional neural networks. Now, 2-point statistics is actually a very convenient way of representing microstructures. What I'm going to do now, I'll just go over it very briefly, and then in one of the subsequent lectures, we will get into the details of the 2-point statistics. We'll get into the mathematics of the 2-point statistics in much more details. But right now, let me just give you a physical feel of what this 2-point statistics is. So essentially what we are doing over here, we are trying to find the correlation of one point in the microstructure with a different point in the microstructure. So what we do, we have our reference cell. So in this case, the reference cell happens to be the white cell. And then we start moving in well-defined directions. So here we are moving diagonally. So we move for well-defined directions for well-defined number of steps. So here we are moving diagonally and we are moving along 2 diagonal lengths. So starting with this reference cell, which over here is, let us say, a white cell, I reach another cell which also happens to be a white cell. And then we can basically say that if both the cells are of the same type, then I represent that with number 1. If the cells are of different types, I might put a number 0 and so on. If I use this cell as a reference cell and then move along the direction of yellow arrow, I am basically moving the same distance, but I am reaching another cell which is a black cell and not a white cell. So the correlation between this cell 1 and cell 2 and cell 1 prime and cell 2 prime is now going to be different. So if we start doing this type of correlations, we can actually capture the spatial distribution of different phases throughout the microstructure. And this is one of the very important things that the 2-point statistics will capture. So just to give you an idea of how powerful this technique is, I am simply pulling up this title of this paper. This is an excellent paper if you want to look into it, how people have actually implemented this 2-point statistics type of concepts into modeling the microstructure. So here, this figure A is basically a figure which shows the microstructure of a material that has undergone spinodal decomposition. So you have this type of characteristic spinodal microstructures, and then once you do the 2-point statistics plotting, this is how the figure starts looking at. Now, depending on how you are actually mapping the correlation, you could have something like this, or you could even have an inverse plot. And what you notice, the difference between 2 plots is basically the intensities they have now been reversed. So we will get into discussing this type of methods in much greater detail as we move forward with the course. But over here, this is really a nice example where 2-point statistics have been used to capture the microstructure of the spinonally decomposed material. Okay, so as you are using the 2-point statistics, essentially what you are doing is you are building up a wealth of information which is associated with every single image of the microstructure. If you remember, we said that when we are looking at the structure of material, we can actually use images as a good way of capturing the structure at different levels. So at the microstructural level, if you take a scanning electron microscope image or an optical microscope or a TM image, that image is going to be divided into a bunch of smaller and smaller cells. So essentially with each of this cell or each of this pixel, basically I have a wealth of information that is associated in terms of the correlations that I get from the 2-point statistics. Going further with this type of technique, the next logical step would be convolutional neural networks, which we will come across. And so the idea over here is once you have so much of information stored in each of the pixel, you would have too much information, in fact, to process very usefully. So one of the steps we'll have to do next is to do a principal component analysis, reduce the dimensionality of the features describing the microstructures. All of these features are actually coming from the 2-point statistics. And then once we have done the dimensionality reduction, we go ahead and do the convolutional neural networks. So this is one way of representing the microstructures. There's another very useful way which has its roots in the graph theory, and that is something that we are going to look at the next part of this lecture. Thank you.